I'm wondering what the interest is really of the group. I know Leon, and he's interested in precision astrometry, and part of that is plate solve work. Um, Everybody else interested in the same thing, or um, just general purpose plate solving, or what?
I'm
I,
interested in
I,
both. Go ahead.
go ahead, Pat.
No, I was just going to say I'm interested in both. So,
Yeah.
Yeah.
Right.
Yeah.
Certainly, what prompted my questions was precision astrometry and the photocenter idea. And it just seemed like an intriguing way to do some useful observations and research. And so, but I think understanding how your plate solving technique works and how to use it is certainly, we need to do that.
Okay.
Dave, I'm interested also in using plate solve to plate solve our guide images on our new spectrograph we're playing with to see how well it works.
Right. Good.
Oh, by the way, I tried plate solve 3.66 on a smaller field. It was about 10 arc minutes or so. And in the Milky Way, it seems to work just fine. Of course, if you don't have many stars, then it isn't so useful. But Pat and I are going to try it out on Barrow to see whether it works with his 1600 camera, which would make the calibration phase a lot easier than the drift alignment.
Right. Rick?
I'm intrigued by the idea that maybe you can get 10 times the resolution of speckle for multiple stars at once. That's just, that's mind blowing.
Right. Okay, well, so a brief history. I started working on plate solving, I think it was around 1999 or 98 or 99. And I came up with an algorithm that worked well if you had an initial guess of the sky, right? Of where you were pointed in the sky. And that used a very strange old catalog called the Hubble Guide Star catalog. And you remember, and it was a very weird animal. First of all, it was organized in a completely kind of arbitrary way, and there were in triangles and weird things. And there are many actually sections of the sky that I found that were missing in the catalog. These strange thin triangular regions. And I had a long conversation by email with the guy that developed the catalog, and he realized that he had some trouble with it, but it didn't matter to him because for what he was using it for. Then I discovered UCAC3, right? I think that was the next one in line. That was a great catalog. And then that was superseded by UCAC4. Wait, maybe Tom, do you remember what the acronym stood for now?
The UCAC, you mean?
Yeah, UCAC.
I can't remember, Dave. I'm sorry.
I don't remember either. I can't remember what it stood for anyway. So, but it was a beautiful catalog, and it still is. It's very useful. And I've recently made a catalog from Gaia DR2 stars, which I haven't. I'm less and less capable of doing difficult and detailed software stuff as the brain ages. Your memory. I think the brain is actually all memory. I don't think there isn't much more to it than various memory processes. But anyway, the memory part of it is less effective, which means you forget what you were doing or what you were, you forget variable names and lots of other things in complicated software. So I don't know if I'm going to be able to, actually continue this work for too much longer. But anyway, let's talk about what I've got so far and where we can go with it maybe. And we'll see. So
Dave, for the UCAC catalog is USNO's CCD Astrograph catalog, UCAC.
USNO, right.
Right.
And
Right.
that's based on the APAS sky surveys, right?
The photometric data in it is, yes.
Yeah.
Dave, is that UC4 in your Kepler directory?
Yeah, that's UC4.
Okay.
So, so PlateSolve has been a pretty good success for me. PlaneWave uses it in their software, and Dan Gray uses it in SciTech stuff, and other people have used it to do other interesting things. But it's not widely distributed. I don't know if I should have or not, but I didn't because I kept a lot of things proprietary for PlaneWave and for Dan. Nonetheless, it's a useful tool. It has holes in it that should be fixed. There's a lot of things I would love to do with it, but I don't know if it'll ever happen. The way it works, let me, okay. How to describe the way it works? That's a very interesting question. A problem. Let me share my screen. And let me pull up, come on, let's open an image. Maybe if I point to stuff, I'll be, oh, well, that's, let's go to where? PlateSolve images. By name. There's a lot of stuff I've done with testing. You know, you got to test plate solving like all the time. You're always getting new things happening. You know, there's new cameras, and focus run is interesting. Good. I can use that later. Right. There's a lot of stuff to show here, but let's just do something. One of the things I do, which is kind of useful, is I make synthetic images by actually computing an image based on the catalog itself, right? And a lot of the testing I've done is with synthesized images or fake images. Here's a fake image that you'd be hard to tell it wasn't a real image, right? It has Gaussian looking stars, it has noise in the background and so forth. Let's see if this will plate solve. I don't remember. So this is a 10 by 8 arc minute field, very small one. And we've got center coordinates here, so it should solve fine, yeah. But if we get rid of the center coordinates, in other words, now it doesn't know where in the sky it's pointing. So it's got to use an algorithm called an all sky algorithm, which was, I think I was the first to develop this. This was in the early 2000s. And I did this because of PlaneWave. I mean, we had the dream of being able to plop down a telescope and you don't give it any information at all. You just turn it on and hit go, and it figures out where it is and it aligns the telescope and all of that. So let's see if if this will work. Well, that's good. So I tested the routines a lot using these synthetic images that I created. Big ones, small ones, huge ones. I developed an algorithm for Celestron that they use today in their system called, what is it called? Starline or something. And that was very successful. They have a kind of an off axis, or they have a separate camera. And that camera moves with the telescope and looks at a fairly large piece of the sky and so forth. I worked with a couple of engineers at Celestron for a couple of years, and we got that to work. So it's been pretty successful. So this all sky alignment procedure is quite interesting. And I'll give you a little bit of how the algorithm works. It's complicated, so please bear with me for a sec. To do all sky, okay, so the basic algorithms at the time in the early 90s were 3 stars. And what you did was you took triplets of stars in the catalog and you took the distance between the stars. So there's 3 distances, right? And you kind of normalized them to maybe the longest distance or to the average distance or whatever. And then you had 2 unique numbers that were the fractional distances between the stars. So that was scale invariant. And it's also rotationally invariant, right? You could rotate this image and those numbers don't change. So now I have a pair of numbers, 2 numbers that describe 3 stars. And if I take every triplet of stars in the image, I get a bunch of numbers I can use. And then I go into my own image that you've taken, and you do the same thing, right? So you do it for the catalog and then you do it for the image, and you look to try to match those pairs of numbers. It turns out that that's perfectly good if you have a known starting, or you're close to the starting coordinates, because you can do an iterative search. And that was the first version of Plate Solve that I wrote, and that worked very well. It was very popular, but it doesn't solve the all sky matching problem. If you want to do all sky, you've got to do those triplets for all of the pairs or all of the triplets in the sky that you're interested in. And it turns out that there's too many matches. So you get, if you do all sky and then you sort that triplet, the numbers that you get from the triplet of stars, if you sort those and you search, and it just doesn't work because there's just too many what I call false matches.
Dave, the matches have to be with some tolerance, right?
Yeah, there's a tolerance.
And so the catalog that you use has to be corrected for the current proper motion and parallax at the date of the time of that you're doing this, right?
Not parallax, because parallax is typically
Oh,
in
yeah,
the milliarcsecond range, which
that's too small to have to deal with.
right. But certainly you've got to correct for proper motion, because proper motion can be tens of milliarcseconds a year, and over a period of years that can accumulate to a large enough number to worry about.
Okay.
Fortunately, the AC4 catalog comes with proper motion, so it's all easily handled. So anyway, the problem is that there is a tolerance, and the correct tolerance is about 1 or 2% on each one of these distances. And that's doesn't seem very much, but when you've got 100 million or more of these entries in your catalog, that turns out to be like an impossible problem. So then the search algorithm just doesn't work fast enough to be able to handle that problem. So what I did to do all sky matching, or as people say, initialization free matching, so you don't have to give it any information. I wonder if this image will work if I don't give it an image. Usually the image size, right? At least roughly. But let's see if it'll work without any information at all. So now, yeah, well, that was fast. So it worked again without any information. So that was the goal of the thing. And the way that this plate solve works, this is plate solve 3 and higher, 3.0 and higher, is instead of taking a triplet of stars, I take a quad. I take 4 stars. So, and I measure the distances between each of the stars in the quad. It turns out that there's 6 of them, right? And I normalize in a special way. I take the longest distance and I make it set to 1, and then I have 5 parameters that describe this quad. I then order them in a very special way. And the reason I have to order them in a very special way is after I find a quad that matches in the catalog, I've then got to go in and find those 4 stars in the catalog itself. And to speed up that process, I have to know which distances corresponded to which star. So if you think about that for a while, you realize that that's a big headache. Knowing the distances and ordering them, you know, from largest to smallest, well, that's easy. Anybody, but ordering them in a way that you can recover which star it was is a different type of problem entirely. So I did that, and I then searched the catalog, and now instead of having 2 parameters that I need to match, I've got 5, which is way better. It cuts the number of false matches, false positives, down from millions before to, you know, tens of thousands, and tens of thousands is a workable number.
Dave, are there more or fewer quads than there are triangles?
Yeah, there are few. Well, I mean, that depends on how you organize your catalog, but there are actually more quads in my catalog than there are triangles in my triangle catalog. I actually make the triangle catalog on the fly now because there's no use. I'm not doing all sky, but I have to pre-make these things I call orcas, or ordered quads. So the orcas are pre-made and they take days to generate, right? Some number of days of just crunching to generate and to organize and to sort and so forth. But then when you've got them, you know, you've got them. So
you can do that for any catalog.
So I can do that now for any catalog. And it works perfectly well with Gaia also. But, you know, I don't think there's a need to do it with Gaia. I'm not sure. We can talk about that. Anyway, that's the nuts and bolts of it. It's pretty simple. You make these orcas, and you pre-sort them in a way that you can go do a easy lookup. And then the next step is, once you've found an orca that is below your tolerance criteria, then you've got to go in and add stars to validate the solution. So now you've got, say, 10,000 orcas that match all over the sky. They're not true matches, and one of them is a real match. So now what you do is you add a 5th star, and you calculate the quads based on that 5th star, and you have to find them in the you have to find in that star in your catalog. I misspoke. I don't actually recalculate new orcas for the 5th star. I just compute the location of the 5th star, and then I go look for it in the catalog. And if it's not there, I start again and with a new orca. You get the idea. It's a complicated bunch of stuff, but it ends up working pretty well. And it took quite a long time, as you might imagine, to make it work. I had some really bad days when I could not figure out why it wouldn't, work. But eventually, you just keep at it and it works. Okay, so that's kind of the heart of the routine. Then there's a bunch of other stuff that I do. I calculate all of these things and display them and so forth. So let's bring up a real. So this was a synthetic image. It's supposed to work because I cooked it up. I can bring up a real image, maybe.
On the image, what is the difference between the red markers and the blue ones?
Oh yeah, that's a good question. Here's another one. We'll plate solve this guy. Okay, so the red, if I can remember, let's see. Extracted. Those are all the stars that were extracted. All the blobs that were extracted. I didn't tell you one of the interesting, crucial features of it. You've got to first extract the stars and calculate the centroids. So I forgot that detail. It's a hugely important detail. And the way you do that makes a big difference to the accuracy of the plate solution.
Are you
Let me
using
bring
source
up a real
extract, Dave?
image. Instead of fooling around with these test images, let me bring up a real image. Some really bad ones that I've got so many images that I wanted to make work. By the way, Lisa is the program that I wrote for Celestron. And Lisa stands for Lost in Sky algorithm, which is what the Celestron folks wanted to call it. So let's see if I can, and this is what their images looked like. They have a very wide field camera with a little 50 millimeter or 40 millimeter diameter lens and a little webcam, and it's very wide field with very low resolution. And this is the kind of images you get out of it, okay? And I wonder if we can plate solve this. Right, so let's see if it'll do it. Well, okay, yeah, so look at the size of the image. It's 6 by 4 degrees, 7 by 4 degrees. So it's kind of a monster. Let's see if that plate solved. Now it's searching the catalog. Nope, and was not able to match that. I don't know why. Maybe I have maybe I have some of the parameters incorrect for this large field. I don't know. I'm not going to worry about it right now.
Hey, Dave,
Yeah.
I guess I didn't hear the answer to the question of the blue X's and the red X's.
Got it. Right. So these are the red crosses are the extracted stars.
So they exist in the catalog.
The independent of the catalog. These are the stars that were extracted from the image. Okay.
Are you
Okay.
And it
using
shows the
source extract,
centroid,
Dave?
shows the centroid location, right?
Are you using source extraction, Dave? Source
No,
extract?
this is my own. I tried S extractor
Yeah.
and actually many times, and it gave me results that I didn't like. So I wrote my own routine in the
Cool.
end.
And
I
what are the
also
blue-
used another one from, where were those guys? University of New Brunswick or somewhere, unexpected. Anyway, I got a couple of other extractors, and that one actually worked better than source extractor, but I still didn't, it wouldn't handle a lot of cases that I had to handle. One of the cases I had to handle were stars with very bad aspect ratios, like this one, for instance, or much worse. There's some images from the Celestron folks that were truly horrible. And none of the extractors would work well like on that thing. But PlateSolve does, because I had to make it work with it, So Okay, so the extractor
This-
has found this star and its centroid. Now, the blue cross means there's a catalog star there.
Ah,
And what is it? The yellow circle means that it's matched that star, that extracted star to the catalog star. Here, you could wonder what's going on. I don't know what's going on. That's your guess is as good as mine, but it got something. So yeah, so the stars are kind of, you know, in that little Celestron thing. They had to make it for, whatever they sell it for, $99 or something. And, they're under a real pressure for commercial sales that has to be below a certain price or people won't buy it. So we had to make it, very inexpensive. So it's got a really cheap lens and a really cheap webcam in it, and that's the way it works. Okay, so we go to some other images. This might be a good place. Yeah, so I had to make it work for another guy with images that looked like this. I won't tell you who these folks were, but this is these are really, really poor images. Look at the noise. There's I had to make it work it has to reject all sorts of stuff like this bad stuff and so forth. So the star
Hey, Dave.
extraction, yeah.
I don't think your screen's updating. What we have still is the calibrated 3210 NGC image.
Oh.
I'm seeing it updated.
I'm seeing
Oh,
it.
really? Huh.
Yeah.
Okay.
You
must be-
should see an image called Andy 2 18/27.
Yeah.
No?
I see it.
Yep.
Oh, okay. I'm sorry. It's my problem, not yours.
Okay. So let's plate solve this guy. So, there's a really interesting example of what you've got to do for effective extraction. Look at this blobby mess, right? That's actually a star. Um, hard to believe, but it is. So, the centroid turned out to be in almost exactly the right place with the catalog. And that's the beauty of centroiding. You can get all sorts of weird looking lumps, but the centroids usually are pretty close to the truth. And that's what led me to the interest in precision astrometry. Okay, so you get the idea. So that's, let me stop there and you can ask some questions if you like. Anybody have any? Okay.
I got one.
Yeah.
The sequence numbers, the second column in the photometry, yeah, those guys. What are they, and are they unique with the matched images or with matched stars?
What are they? They're my own numbers. They correspond to the number in my catalog because,
Okay.
yeah.
So there's as we go through a sequence of images and plate solve them, that number will be, assuming the plate solving's worked on each of the images, that number will be consistent with
They're
the same
unique.
star from frame to frame.
Yeah, they're unique. They're
Yeah,
in my catalog.
okay. Got it.
Um,
I'm guessing
By
this
the
is
way,
the next logical topic. How do you deal with the distortion in the images, especially on a
that's a
cheaper
really
lens?
great question. As you
Yeah.
guys know, optical systems can have kind of severe image distortion. The photographers call it either pincushion or barrel distortion. And it's typically third order. In other words, as you go out from the center of the image in radius, instead of, let's say that was 1 unit in radius uh, on the sky. The true distance on the tangent plane is 1 unit. Well, it might be 1.1 units with a highly distorted lens. So that creates a big problem for plate matching, right? Because the orcas are distorted. And then when you try to add a fifth star, well, that's distorted and so forth. And there's a bunch of tricky stuff in plate solve that takes care of that. I actually have to do a special type of fit when I'm adding the orca. I can't do anything about, but it's usually a fairly small piece of the field. Like it would be those 4 stars. And this field might have several dozen orcas, that were computed, but they're all fairly small. They're typically 1/5 to 1/10 of the size of the field. But then when I start adding the 5th star and so forth to look for the bigger match, I then have to do this 3rd order distortion match at the same time. And it's a bunch of mathematical fitting that you have to do. It's a great question, and there's a lot to it inside of plate solve. And it was truly terrible in the Celestron. Imagine a little 40 millimeter achromat that purchased from China for a couple of bucks or something over such a huge field of view. It had enormous amount of distortion. And, the only way to get it to work was to actually model that distortion in the fit.
What do you do about all the blue there that are not matched? Does that concern you? And
Well, there was no star extracted.
yeah,
So let's go look
okay.
at this. So there's a catalog star there,
Yeah,
right? But there's no extracted star in the field of view because the image wasn't deep enough. It's really a 40 millimeter lens
yeah.
with hardly any light. So it's just, I got just enough stars
Yeah.
to make it work. So plate solve has a feature where once I plate solved it, right, I can use this little icon, which is called the photometry tool. And the photometry tool allows you to take a look at what you got. So let's take a look at this star. And I've got automatic check. So what it's actually doing is it's automatically computing the correct aperture to use to do the photometry on that star. And so let's look at it. It shows you the mean background and the background standard deviation, right? It shows you the object, signal to noise, and the computed magnitude of that star based on the UCAC4 catalog. And a bunch of other stuff. The size of the star was 4.5 arc seconds, roughly, and so forth. So the dimmest star in this 6-second exposure that actually produced a match was probably this guy, about 15 mag, which, is characteristic of the size of the lens that they used for the. Okay, so what else? Anything else about this? There must be, it's actually better to answer questions than probably to keep going through the. All right. Then let's take a look at some of the other things that plate solve can do. Once you've extracted an image, you can show the extracted values here, and you can send this text to a clipboard, and it's in the format of a CSV file. So if you want to do further work, you can use it. You can use this information and just send the text to a clipboard to the clipboard, and then you can put it into Excel. And I'm sure you all know how to do that. And in Excel, you'll see the header, and it'll tell you all of the good stuff, the things that you actually need to know. Whoops, you know what? I don't have the catalog number of the star. So actually there isn't everything you need to know. Okay. Well, anyway, you get the idea. You can use that. And you can also calculate coordinates with this form. So a lot of people use this for asteroid work. And, let's say that this guy was actually an asteroid. It was really a catalog star. But let's say that you found this and it's an asteroid. By blinking images or whatever, you found an asteroid. And you want to know what its position is. Well, over here in the in this box, photometry, astrometry, it'll tell you its position. But suppose you want to look for something that should be there and you can't find it. You can actually put in the J2000 coordinates here, and it'll produce an X and a Y pixel location on the image. That's quite convenient for some work.
Can you go the other way, Dave? Can you take one of your images and click it and have it convert that to show you the star it came from?
Well, that's what this does.
Yeah.
It goes
So-
either way.
You can also, it works either way. It works both ways. There's also some other stuff in here that is useful. Probably the best thing to do, though, is to complete the plate solve stuff. This thing shows the image orientation. This is quite useful in many circumstances. So it shows that in this image, north is up and east is to the left, right? But it can turn out that if you have a different number of reflections in your telescope, this can be mirror image. So north could be up and east could be to the right. And that's important to know. And I've caught a lot of errors that people were making in other things that they were doing just by looking at the orientation of the image. It can be totally confusing, you don't know what you're doing. Okay, so let me think. So this symbology or whatever, iconology or whatever, you can turn it off by hitting that blank button. Kind of makes sense. And you can turn it all back on by hitting these individual guys. If you want to know what's catalog, extracted, star number, and so forth.
Dave, another question. Could you describe the way you choose photometric apertures, the inner and outer size and all that
Yeah, that's a
a little bit?
question. So let's go take a look at that. The way I choose a photometric aperture is the following. It's an iterative process. So I start with the current centroid position. And so this is the automatic part, not the manual part. The automatic part does this. I start at the centroid. I go 3.5 sigma out from the centroid, and I compute the new centroid and the new RMS diameter. And then I iterate that until it stops changing. In other words, I use that new RMS computed diameter to set the aperture at 3.5 times that diameter. So basically, in the end, you get an automatic centroid that has you get an automatic aperture for the star measurement that has a diameter of 3.5 times the RMS diameter. Then the background annulus is then, what is it? 5 pixels to, sorry, it's 5 pixels larger than that to 10 pixels larger than that. In other words, it has a band, I think, of 5 pixels under normal circumstances. It's something like that.
So the star diameter is kind of like a growth curve that stops moving.
Yeah, it's the growth curve. And when it stops moving, you've iterated enough times, and it does that individually. No, what it does is it does a global average of that across your image, and that turned out to be important. So it's not on a star by star basis.
Okay, so all the stars would have the same size.
I think all the stars have the same aperture. But you know what? I'm going to have to go look at that. That's an interesting question. If you really want to know, I'd have to look at it.
Well, if you had another close by star, you would see a bump in the growth curve and have to go larger to include both of them.
Yep. You know, that's part of the problem of and source extraction, you know, S extractor should have taken care of that problem, but I think it's so complicated, the problem, that it doesn't work very well with highly elongated and lumpy stars that we often get, right?
Have you ever thought about in the bispectrum tool to use a sort of an automated radius? Or is there one already there that I just don't know about?
Well, bispectrum is quite different. Bispectrum, I do other things. So, but that's all done in the spatial frequency domain. You know, I use a Gaussian high pass and low pass, and that I tried for a little while to automatically optimize that, Rick, but it turned out to be an incredible mess. There's just so many things going on that the human eye is quite a bit better than I could ever make it work, you know.
It seems like there would be a lot fewer chance. Well, in the first place, you only have one example instead of the whole field.
Mm-hmm.
So there's more chance for error there, I suppose. And if there is a noise in the background or a second star or something, it's hard to tell the difference between a little bit of noise and a really faint star.
Mm-hmm.
And well, I can see there's lots of issues there. So
yeah, there were enormous number of issues. I didn't in the end know what to do, so I just had to leave it. You know, the user has to take care of that.
Even though you're dealing in the Fourier plane and all that, you still have to come back and make measurements sort of pixel by pixel, I suppose. So it could be converted. Well, I mean, that's what you end up doing, right? You describe the diameter you want in terms of pixels,
right?
And then it does the photometry. So.
Yeah, you know, there's a one-to-one correspondence between the Fourier domain and the image domain. So whatever, but yeah, it turned out to be an intractable problem at the time that I was thinking about it. Maybe now that I've had years of experience with it, I could do something better. But another problem with the extraction routines that I tried was that stars change their characteristic across the field of view. You know, as you know,
Sure.
Coma and astigmatism and so forth, off-axis astigmatism, is going to appear differently in different parts of the image. So in the corners of the image, you often get a very different profile, PSF. Well, these images are so poor that I really shouldn't use.
And at the same time, the centroids will change, right?
And with Coma, the centroid changes. Yeah, as you probably know.
Do you have some examples from a good telescope, like Pat's stuff originally?
Well, here's an example from a plane wave telescope. This was taken really long time ago. I don't know. Let's see if it's, no.
Yeah, I was going to ask, what happens when you're dealing with galaxies? You just ignore those?
Well, let me show you what happens when you're dealing with galaxies. So sometimes,
You get 'em.
and in fact, you get catalog stars inside of the galaxy probably by accident. You know, the catalog was generated automatically. There's probably there's no target, there's no star there. But I took what I got. So, that's the best kind of that you can do, you know.
Dave,
So
back to your photometry just a second. How do you handle partial pixels?
how
Are
do you
you,
handle,
you're using a circular aperture, right? So how do you handle partial pixels that with that aperture would go across?
right? That's a really good question. So if there's a pixel, I'll do this one. So if the center of the pixel is inside of the radius of the aperture, I use it. And if it's outside, I don't use it at all. So,
Okay.
I'm not slicing pixels at that level. But what I do, of course, is when you take the centroid, you're using the number of ADU counts in each
Sure.
pixel. Right?
It's sort of a weighted centroid, huh? Weighted by pixel location and value.
No, it's not weighted by, well, when you calculate the centroid, you're using the XY value of the pixel location when you're calculating the centroid.
And
you
the brightness.
And the
and-
brightness, right. And you're
Yeah.
multiplying that. So in a way, you're weighting it with the brightness.
Yeah, that's what I meant.
But, if you happen to have an aperture here, you catch a hot pixel. So it's always better to do a calibration, at least a dark subtraction. When you're using plate solve, you'll get more accurate results than you always do, because you're going to kill a lot of the junk that's due to the sensor.
So you think
Right.
for accurate astrometry, you really need to do that all the time?
Well, yeah, you're not going to get accurate astrometry if you don't
Okay.
do a
because
good
of all
calibration.
because of all the hot pixels.
Right. I mean,
At least because of-
we could talk about that problem for days. That's a very interesting topic to me. But
But Dave, do you recommend in your calibration process removing the hot pixels or not?
well,
They should.
you should theoretically, right? That's part of the calibration process, is to, if you've got a hot pixel map, then you should use it. If you don't know how to do
Okay.
that, then you can kill the hot pixels with a hot pixel routine. That's going to be less accurate because you'll be changing some of the pixels inside of some of the star apertures where you probably shouldn't be. Depends on your hot pixel algorithm. So
Yeah. Okay.
I have a hot pixel algorithm. Let's apply a hot pixel filter. I don't know. What did I do? I mean, maybe I don't have that working. Huh? That should have killed this guy, but it didn't. Okay. That's the problem with writing your own software. I don't do enough testing. I don't release this widely because people devote their lives to this stuff, and I just don't have the time or the inclination to devote my life to it. But it is a useful tool, and the stuff that I have done in it works really well because I've kind of optimized it for accuracy.
One more question.
Yeah.
When you click on the menu items at the top, you can have the catalog star name shown.
Yeah.
But this is the catalog you made, right? It was like a 10-digit number or something.
Yeah.
Would it be possible to convert that to another known catalog, for example, Gaia? Or could you use the Gaia catalog?
I do. I have the Gaia catalog. I haven't fired this up for a long time. To think about where to find it. Let me see. I'm surprised it's not. Let me think. And Gaia Explorer, I think. We'll see. So this is how I write my stuff. This is a program called Visual Studio. It's a free software from Microsoft. It's probably the best thing they ever did. It's an amazing piece of work. It's just a gorgeous, it's just a gorgeous piece of software. It's probably because it was written by people who love it, you know, and Windows is another story. Let's see. I think this is it, but oh my goodness. It's generating. Okay, so I'm sorry, it's generating error. That's embarrassing, but okay, that's the way life is. I have to go into it and find out why it's now generating errors. That happens all the time with Microsoft stuff. You get an update and you got to go repair something. And it's been a year or two since I've goofed around with it, about a year. So I have a program that allows you to place to generate a local Gaia catalog all the way down to, you know, 20th mag, whatever Gaia goes to 20.5. It's pretty complete to mag 19 and it goes to something like 20.5. And all of that stuff I've never released it because people haven't really been interested, but I see Leon is quite interested in this whole thing.
Well, this is a bit more specific. I can quickly talk about it since it's probably relevant for everybody here. What I was thinking is, from my old telescope, I now have what I think of raw images, it's like 700 gigabytes, taking it over a long period of time.
Mm-hmm.
And all this data is just sitting around. Now, if something interesting happens in one part of the sky, let's say supernova, that's what brought me to this idea, then I should be able to go back and perform photometry on that previously insignificant star. But
Sure.
the problem is I currently have no means of checking my images if they contain the star, if I ever observed anything by any chance.
Got
So
it.
what I'm thinking is I need some software. I can probably throw together multiple softwares myself and get a result, which can identify a star in my image when I tell it to iterate through all my images. And this could be overnights. It's just, can I use my historical data, which I've taken, to still be useful for anything modern?
Yeah, that's
Whether
a
it's
beautiful.
asteroids, like an asteroid crossing that image at that time, which wasn't known before, or a nova.
You know, that's a really beautiful question. The answer is yes, we could easily accomplish that. So let me show you. This is a later version of Plate Solve that I've been working on, 3.70. And it has a tool called astrometry, and it can analyze an entire image, a folder of images. So you could put a collection of images in this folder in a folder, and it will analyze all of them. And let's see what it'll do. Well, let's browse for a folder. I mean, I could do this one, but that's not kind of interesting. Let's go to, there's Leon. Here's your first 100 images that you sent to me, right? There they are. So I can open that. I can align and combine if I wanted to, but it's actually not a good idea for precision astrometry. But I could give it an initial plate solution if I wanted to, if it couldn't find one on its own. But almost always it'll find a, valid plate solution, even if it doesn't have starting initial condition. And I could put it in a results folder. So let's put it, let's actually make a new folder. We call it test results. We'll give it that as the results folder, and we can just let it go. And you see, I've got a Gaia catalog actually working on this. So that Gaia catalog is enormous. I think it's around 150 gigabytes. So I have to be able to transmit that to people that want to use it, but I don't think that's a problem anymore with, with the internet. Maybe you can tell me, Leon, is that going to be a problem?
No, I sent you an email on this.
Yeah, I read it, but yeah.
Dropbox was my idea.
Yeah. And I use Google Drive a lot. I could upgrade to a terabyte. I just looked at it after I wrote that email to you. So there's ways of doing this. So now what it's done is it's gone through and it's plate solved those images. They could be anywhere in the sky. It doesn't matter. And if you've got starting coordinates in the FITS header, it'll use that. But if you don't have starting coordinates, it'll try, all of its tricks to find a match. So let's stop this and go take a look at the results. Okay. So you've seen this already. I've showed you this stuff before, but it's worth repeating to see what you get. So let's go into that folder. And there's the test results. So it did this, and they're all CSV files now, right?
Now these files, Dave, these files are different than the ones if you did the sequence, solved a sequence under the tools menu.
Solve the sequence under the tools menu.
If-
Well,
if you
anyway, this information is actually the same, I think, as the one that you're talking about.
Yeah.
So it shows you the number of match stars and so forth, and there they are. And it has a sequence number, which now I can directly relate to a Gaia. I could find the Gaia star related to this. But Gaia doesn't really have, okay, so let's break the problem down into its fundamental issues. Do you or can you find the J2000 coordinates of the objects of interest in your set of images?
Are you asking me?
Yeah, I'm asking you.
Yes. You
Yeah.
mean by plate solving them?
By
Or-
what?
You mean if I can find the coordinates of the objects by plate solving them?
No. What I'm asking is let's say you have 10,000 images that you've taken. I'm just making it up. And they're from all different parts of the sky. And all of a sudden you find out that there was a supernova that you'd like to go look at. And you know the J2000 coordinates of the supernova, right?
Right.
So there's lots of things we could do, but a very easy way is, you get RA and DEC out of these images, right? There's the RA and DEC of each one of the extracted objects in the images. You could look at you could look at these numbers and apply a tolerance to them, then of an arc second would be probably good enough. And you could search every one of your images for that location in the sky, and we could easily do that automatically. So what I'm trying to say is a catalog number from, what's a good example? When we used to use catalog numbers, I don't know. We used to use catalog numbers before we had Gaia, before we had UCAC4, we had every star had a catalog number in that catalog but now we don't do that anymore because the catalog numbers are they're totally meaningless. You now look for RA and DEC, Anyway, so I could tell you let's go one step further and do this. Let's go back to plate solve. And let's go to make a summary from astronomy. I should call this something else, but those results that I just created, the plate solve analysis, I'm going to now go to that folder. There it is. And I'm going to select that folder. And I'm going to save what I call an observation. And we could modify this very easily. Call it something clever like obs. Okay. And it finished. It found 141 stars. So we'll go navigate to that. And it's inside of here, it's inside of here, and there's the observation. And now I've got the thing that I talk about a lot. I've now calculated statistics for each one of the sequence numbers. So now if I had a bunch of images of the same part of the sky, like you're doing photometry, then we could do something more elaborate, like we can calculate the SEMP. There it is. Okay, standard error of the mean position.
Yeah, so this is built into 7.0, huh?
Yeah, and I haven't finished 7.0 because I haven't worked on it much in the last month or two. But then we can do something else. We can, well, I don't have the stuff in front of me here, but I can assign a Gaia catalog, my own Gaia catalog number to those objects too, and you've got the RA and DEC. So it's a very simple matter. If you had a CSV file that you could create that had all of the objects of interest, we could plate solve all of your images at once, one time you go through them, and then later we could process each one of those CSV files. I save everything as a CSV. We could process each one of those CSV files looking for the thing in particular that you're interested in. And it's a very simple exercise to do that.
I wish this would be done more often. I mean, there must be so many telescopes who have done so many observations over the years. It's just so much data which isn't available regularly.
Yeah, how many gigabytes do you have?
I think 700 of images, though that was with the 600, so the image files are massive. And I've kept all my calibrated images as well, so the hard drive is in the terabytes, but of actual raw images, it's I think 700 last time I checked.
Okay, well, at 3.66 has a rather nice plate solve multiple images in the tools menu. Okay. And it actually has a little explanation. So if I browse to an image directory, let's go to something more interesting. I don't know. I'm just gonna, no, that's not a good example. Let's go to, I know what we'll do. Images for plate solve testing, my favorite. And here's the, Dan. Standard plate solve image set. This is a really good one. So I'm going to use that. And this could be a folder where you've got all of the images that you want to plate solve. And let's save the plate solve results in a new folder. That's kind of important. So what I'll do is I'll go up a level. Yeah, that's probably a good place to. And new folder. And we'll do that. And now we're going to save the extracted stars, and we're going to save the photometry data. And we can even resave your files with the correct world coordinate system, which is very handy. It puts it in the FITS header, and then you'll have it forever. But let's not do that right now because it's going to resave a bunch of images. And let's just hit start. So now it's going through every image and it's doing a plate solve, okay? And we'll let it do a 2 or 3 image and then we'll stop it and we'll take a look at what we get. Okay. Now, let's go find that thing. If I can remember what I was doing. Oh, test results. Okay, so now what it's done is it's created CSV files for a bunch of different things. One is photometry data. So let's go look at the photometry data. So this is that same stuff that you're used to seeing, but now it's done it for every image in the folder that you selected. So now you've already got the RA, the deck, the and all of the important stuff, the total signal, which is hugely important, right? The SNR, the RMS diameter, and so forth. Lots of important stuff.
So the next thing I wanted to do was to combine each of those files, the photometry files for the sequence, and understand the statistics of the sequence. And what you're saying, I think, is that that's in 7.0, or you have that ability in 7.0, right?
Right.
But is there an easy way to do it just with the image, with that file, the photometry file from each image in the sequence?
Absolutely. If you know how to manipulate spreadsheets, you've got the information right in front of you, right?
So it's just a matter of working with the different spreadsheets.
If you want to. I'm trying, yeah. That's a little bit different question, Scott, because I've already got the routines that do that for you. But I'm trying to answer Leon's more,
Okay.
detailed question. Let's look at one of these things and see what we've got. We've got, I think, all of the important information. You've got a sequence number that's from my catalog from UCAC4 if you need it. But there's many cases where it extracted something that it didn't match to anything. There's a case, and I put a -1. And it's got the centroid locations on the image if you need to go look at the image and find the object. More importantly, it's got the RA and DEC in radians, which is the key thing. So you could literally, if you knew how to do a little bit of spreadsheet manipulation, you could take this huge file of photometry data, all those individual CSV files from every one of your image, and you could search around this RA and DEC to find interesting things. And you get a lot of photometry statistics here. You get the aspect ratio, you get the angle of the semi-major axis, the angle of the major axis. You get the background information, the calculated SMR, and the RMS star diameter or blob diameter, okay? Did that answer your question? This is totally easy.
Oh, yes, this is a perfect way of doing it. If I have the RA and DEC, I can just, let's say in column O, I can apply a plus, well, a small tolerance, and then I can search through all my images if I want to. It sounds like here in 3.66, the biggest thing to do here is combine the different spreadsheets into one automatically, but that isn't so difficult.
Right. So then what I do in 3.70 is I take each one of these spreadsheets, I read it in, and I process it in a special way. I look for the same sequence number in each one of the spreadsheets. And that tells me how many times I've observed it, and then I can calculate the detailed statistics. Because each one will have a different, slightly different RA and DEC, right? And that's how I calculate the standard error in the mean position. But for
Yeah,
your,
and you have a piece of code that does that, right?
I have a
mean,
piece of code that
script
already
or
does.
whatever. Yeah.
Trying to think if there's other stuff.
Right, there. I would only have one more question. Let's say I find the target, so I know I observed this star in the past. How would I link it to a specific sequence now? Because in there, I didn't see any file names.
Didn't see any file name. Well, because that CSV file was created from a single image, and I didn't put the file, since the file name is kind of a default attribute of the file, I didn't put it into the, where were we? Wherever we were, let's see, photometry. Yeah. Actually, I did. So there's the file name right here. So you could actually, if you were just reading in CSV files and you weren't paying attention to the file names that you were reading in, you could find it again here. And that would be a brilliant project if you have, I mean, it's a really great idea, to tell you the truth. All of the images you've taken, you could go look to see if you can find some special interesting things in those images that like supernovae or asteroids or whatever. That would be fun. And the plate solving has been done for you. Your hard part is to figure out how to read those images in, and I mean, read the CSV files in and process the damn things to get useful information out of it. It's not so simple. Yeah.
You could pretty easily put all that data into a database and do all kinds of really interesting things, like, I don't know, if you wanted to. It's not hard to do once you get them in a file system that you can actually sort and search.
Yeah.
I've worked with spreadsheets a lot. I'm currently making many of them for the European Space Agency, the project there. But this should all be easily manageable, I think. So
Mhm.
if I can search for everything, this will be great. So I'm really happy that this is possible with PlateSolve. I've searched for this for a while now, a program which can do this.
Yeah, well, and I know it's been an hour and I'm hungry. I want to go get some lunch. We can continue this whenever you want to, if there's more stuff you want to know, but there's a lot of useful information up here too, you know, and we can cover that, but one of the most useful things is if you've got if the FITS header contains information about when the object, when the image was taken, it'll give you a Julian date, which is crucially important for, you know, doing good astronomy. The exposure times, very important. The aperture radius that was used in computing. So this is the global radius of the aperture that was used in the computation plus the background radii. Okay. So this defines, these three things define the aperture that was used. This is the image size. JD helio is the heliocentric JD. It didn't get computed for this image for whatever reason. Date of observation and so forth. So it also tells you the rotation of the plate. That can be quite interesting. There should be, the plate scale should be here, pixels per radius, per radian. So that tells you the plate scale in pixels per radian. Okay, so with this, which 66 calculates for you, you can turn it on and in one evening or overnight, you can do thousands of images and have all of those spreadsheets available and just crank through it then. Then it's whatever you can dream up. Kind of fun, huh? Okay. I think that's enough for today. I hope it was useful. I don't know if this stuff is useful or not. Is it useful?
Absolutely.
Yep, yeah.
Okay. It's fun for me, you know, it's a lot of fun. Let me stop sharing. There we go. And if you want to do it again, I'm happy to. You just have to, whoever wants to be involved in it again, I can cover some of the other things that I've tried to do. Not everything works perfectly, but there's a lot of other stuff that's useful. So
Definitely like to do it again.
Yeah.
you want to do it in a week from now? Oh no, I'm leaving for my desert cabin a week from now. So it'd have to be in a couple of weeks.
Yeah, it'd be fine.
16th?
That would be
It's a Friday the
16th. Yeah,
Yeah, okay.
same time.
Same time. Yeah, that's great.
Good.
2 weeks.
Yeah,
Yeah.
let's do that.
Like-
I'll send out an invitation.
Good.
Thanks, Dave. Appreciate it.
Thanks.
Yeah,
Thanks so much.
very
Dave.
useful.
You're all very welcome. It's great stuff. I love to talk about it.
Fascinating.
We'll see you later.
All right.
See
Take
you.
care.
Bye.
Bye-bye.